But I did note that the clouds off to the east at 5:30, 6 o'clock, even 6:15, there were some really nice developed clouds out there still, probably over by Highway 27, and they were really high. That you could see they were probably 7,000 feet, you know, way higher than what we were seeing on during our task time. Oh, I thought I saw a question. What is your name?
My name is Barton.
Barton. Nice to meet you, man. All right. More questions. Anything goes here. Stump the chump.
What's the green line again?
That's the dew point.
Oh.
That is the data achieved from the actual balloon as it was sent aloft.
That's the actual dew point as opposed to the...
Right, as opposed to the fixed dew point.
Yeah.
Cooling line. Okay.
So it's dry until it gets to where the dew point temperature meet, and then it's wet above that? Above that,
yeah. And that parcel will then cool at a lesser rate as a result of that, the fact that it's condensed.
Yeah. And that gives you vertical development.
That's correct. So if this red line had continued to go like this, that cloud would have been building and building and building until it met that red line. And that's what we'll see today when we look at it today.
Once it forms a cloud, doesn't it just, it releases heat too?
Right, right. And hence the difference in the cooling. So, and I might have some of this backwards, so don't hold me to everything, but. So here's an example. Here's an example. So here's the environmental lapse rate, the data from the balloon of how the parcel is going to cool as temperature or as it rises. Here's a parcel that forms at this temperature here. It's cooling adiabatically. It meets the dew point line before it reaches equilibrium and starts to form a cloud. Now it's going to cool at the saturated adiabatic lapse rate until it reaches equilibrium. And guess what? That's 17,500 feet. So now you've got a nice tall cumulus cloud that's over 10,000 feet high. So that is kind of the genesis of why they created these models way back in the day, was to get a better prediction on severe weather. So it's really a safety thing for the people.
Larry?
Yes.
So how high does that have to go before it'll turn into a thunderstorm?
I don't know.
Okay.
I don't know. You know, I've seen days where the clouds are only 5,000 feet maybe in development, and got lightning and rain coming out of them. And it was a remarkable day because they were small clouds, but they were lined up in streets, and it hadn't quite overdeveloped. But we were driving home, and it's like every 10 miles we're hitting rain and nasty weather, you know, and then it'd open up again and be sunny. So, so my guess is that it doesn't take much vertical development. Depends on the moisture in the air and a number of factors, but. So a dry adiabatic lapse rate, just give you the definition. It's a process in which no heat or mass is exchanged with the environment. So the parcel stays a parcel as it's rising. It's not being fed by anything else. In the atmosphere, a parcel expands and cools, or compresses and warms at a relatively constant rate. So mostly they expand and cool at a constant rate with respect to altitude, and that's that adiabatic line that we were looking at. The rate at which this happens is known as the dry adiabatic lapse rate. I'm going to skip this portion for now, but I'll send it to whoever wants it, and you can have this information available to you. But sometimes you hear talk about the lifted index, and it's the temperature difference between an air parcel lifted adiabatically and the temperature of the environment at a given altitude. So the higher the spread between the temperature on the ground and the parcel that they measured from the balloon, then the higher potential for some severe conditions to develop. So a lifted index greater than 1, thunderstorms are not likely. However, if it's less than -6, then it's unstable and you're going to get severe thunderstorms. And I'll show you an example of that at some point here. This is a good slide. The temperature lines are at an angle skewed and the pressure scale is logarithmic because these choices make quite a few of the variables that we want to examine more or less linear. And that's why we can make sense out of this diagram. The widely used formula for cloud base is a consequence of the differing rates of change of the temperature and the dew point of a lifted parcel of air. So you've probably heard this, the lapse rate, 5.3 degrees per 1,000 feet. The dew point lapse rate is 0.9 degrees per 1,000 feet, so significantly lower. And cloud base is the temperature lapse rate minus the dew point lapse rate, so 5.3 minus 0.9, 4.4 degrees per 1,000 feet. So a lot of what you can do is look at the temperature spread for the day. It's going to be 50. If it's 50 degrees in the morning, 75 degrees at the peak of the day, 25 degree delta T. We're usually, just as a rough estimate, saying divide that by 4. We're going to get to 6,000 feet that day. I don't know if you use that at your site or if you ever have, but that's a good approximation. And summer conditions, it works pretty well. But I like to be a little more precise. Oops. So now, let's see, I'm going to go to, hopefully I'm still online. I'm going to go to the Oz report. And we'll look at Florida for today. So if you go to the Oz report, he's got a good weather site here. It's got sites all across the country. We'll go to the southeast. And then we're going to scroll down. You can see he's got some of the national weather forecasting information, satellite information, blip maps, Dr. Jack, the windcast, and then there's a part that says latest FSL soundings, Quest Air. You see that? Yeah. So I'm going to click on that, and this takes us to, I believe it's the NOAA website, RUC soundings, and you can see the Skew-T diagram here. Oh, and look at it, populated. So this is the part where it's interactive. This is the actual parcel, the actual environmental lapse rate, the actual information that was retrieved from the weather balloon, plotted onto this scale. So upper left hand corner, you can see the wind speed in this portion here, and direction. I don't use that very much. Its wind is in knots. I look over at the right hand side where the flags are, and you can see the direction. So down low, the flags are showing it's southwest, and then increasing with altitude, and the barbs on the flag are wind speed indicators. So if it's a full barb, it's 10 knots. If it's a half a barb, it's 5 knots. So you can see a half barb right there and 2 full barbs. So it's 25 knots at that altitude, which is 7,000 feet. You guys see that?
Mm-hmm. And sorry, the barbs, I'm Ken.
Ken.
Yeah.
What's your last name?
Millard.
Millard?
Yeah,
okay.
Up from Oregon. The barbs, they always look like wind, like windsocks to me, but it's the reverse. The barbs are the base. The unbarbed portion points the direction that the wind is blowing.
Yes.
So the wind is coming from where the flag is to the stem, right?
So I'll put my cursor up here and then you can see, let me get the right altitude here.
You can imagine that it's an arrow with only two vectors on one side.
Yeah, okay, great. With
The
360
reflections
to
of
the
the
top.
side.
So if you see my cursor is now up onto this is the interactive part. And as soon as I put it up there, a bunch of data appears. The first point of data is 28 feet, and so I stopped the cursor at 28 feet because that's generally the altitude that we're at. It lists a number of parameters. Number one is the wind direction and speed, 10 knots at 220 degrees. The shows the pressure in millibars. It shows the temperature in degrees Fahrenheit as well as Celsius. So this, I'm going to scroll down just briefly here a little bit. This highlighted box shows what time of day that